Hello everyone, today we'll explore the concept of hydrostatic pressure, specifically how pressure varies throughout the fluid at rest, and expand a little bit more based on the fundamental concepts we've learned. The word statics is derived from the Greek word statikos, which means motionless. For a fluid at rest, there will be no shear stresses, so the fluid particle will only experience normal forces due to the pressure from all sides. As could be seen from this cartoon, this poor guy is being squished from all directions while he was diving underwater. This is exactly what a fluid particle experiences. Hydrostatic pressure is present in all directions and acts at. Why do we usually have a specific kind of fish live in a specific layer in the ocean and they don't seem to migrate up and down? This is caused by the pressure difference due to the difference in depth. This will be explained after deriving the relationship between pressure and the depth of water. First, let's start out with the general form of the equation of motion for fluid at rest. If you can see here where the delta or del is the operator and P, which is the pressure gradient. What the del operator implies is that we're looking at the pressure at all sides, in this case the Cartesian system, that is applying to the fluid particle. So we'll be looking at all x, y, and z directions, and looking at how the pressure varies across the elements. Gamma here is the specific weight of the fluid, and we're applying this only in the k vector, which is also our z direction. So this is the part that accounts for the weight of the fluid particle. And at last we have this equal to rho, which is the density of the fluid times the acceleration factor. And again, with this factor, we're looking at all our Cartesian coordinates. If we say our fluid particle is at rest, acceleration equals to 0, we could rewrite this equation and show that the pressure is going to be only a function of this z component, k. So what this means? It means we could have a differential form of pressure as a function of z equal to the specific weight of the fluid. So this becomes a fundamental equation for a fluid at rest. The negative sign here indicates that the pressure decreases as we go up in elevation and increases as we go down. If you can imagine yourself in a swimming pool, think about the pressure that impacts on your ear as you go deeper and deeper in water. You could feel that the pressure increases as you go down. If we have a cylinder with two holes with stoppers on the side and fill it up with water, then we take a side view and remove the stoppers. As you can see, water will flow out from both outlets, but the horizontal distance traveled by the water flow are different. For the flow from the upper outlet, as you can see from the pressure gradient on the left side, it's under a smaller pressure, so it won't get as far as the lower one, which is experiencing high pressure. Moreover, as the water flow out, the water level in the tank will decrease, so will the pressure at each outlet. This results in decreasing the horizontal distances for flow from both outlets. We could also think of pressure as a weight accumulation of the fluid. Now let's think of a tube of water we have. If we take a little bit of water and we put it at the bottom, and it's gonna have some pressure associated with that much water. If we think of a thin layer at the bottom of the water, it's going to have a counterbalance force acting upwards. Now if we add more water, the pressure is going to increase because the weight of the water is now acting downwards on the water below it. And since the water is at rest, the force must counterbalance the weight above it. So if we keep adding water, the force is going to get larger at the bottom, and therefore the pressure at the bottom is going to increase. So all the fluid particles stacked on top of each other are going to exert some kind of weight and therefore pressure on the fluid particles at bottom. And since they're not moving, so the force must counterbalance it. Therefore, the pressure at the bottom is going to be much greater than the pressure at the top. Now we know that pressure increases as we go deeper in the vertical direction. What would happen if there is a pressure difference in the horizontal direction? Let's separate a tank with a block in the middle and fill each side up with a different amount of water. Now the pressure difference is created. As you could see, the pressure acting on the same point of the block is higher on the right side than it is on the left side. If we cut a hole in the block, water will flow from the higher pressure to the lower pressure until there is no pressure difference. Now we'll connect two separate tanks with two vessels, both on top and bottom, and fill each tank with a different amount of water. From the pressure gradient on both sides, we could see that the pressure is bigger on the right side at both vessels. If we open the clip in the middle, water will flow from the higher pressure to the lower one, which means from the right to the left. The bottom dashed line indicates the incoming water from the bottom, and the top dashed line indicates the incoming water from the top. Finally, the system will adjust itself until the water level is the same on both sides. For the same system, if we start with a different fluid with different densities on either side, say the heavier fluid on the left and the lighter fluid on the right, you could see even though they're at the same height, the fluid on the left have a much higher pressure than the one on the right. However, the mechanism is still the same, which means fluid always flows from the higher pressure to the lower pressure. As the flow goes from left to right, it pushes the fluid on the right up until it hits the vessel inlet and flows across the vessel into the left again. Again, the system will adjust itself until it sees equal pressure on both sides. If we think of the system in another way, meaning that we're not filling in different fluid to different levels, instead, we'll fill in both tanks with the same fluid to the same height, but heat the tanks up under different temperatures. As you could see, the temperature of the right tank is increasing faster than that of the left. As the fluid is heated up, it will expand. The higher the temperature, the more it will expand. Finally, we'll end up with this configuration. Now if we open the clip in the middle, again the fluid will flow from the high pressure to low pressure, and the system comes to an equilibrium until it sees both sides have the same pressure head. This is how nature works. Air could be considered as fluid in the tank. Warm air goes up as it heated up. Cold air will sink as it cools down. Convection will happen as two air sources are connected by the vessels. However, in real life, there won't be vessels connecting two places together. But this gives you a general sense of how airflow circulates. The systems above all came to an equilibrium state at the end. But in nature, there is another state which is neither unstable or stable, and we call it metastable states. Think of a ball on a curvy path. If it starts on a slope, it will roll down for sure, and it will move back and forth until it gets to a relative low point. You can't see that it's stable, because if it's provided with enough energy, it will move again until it hits the lowest point. While it was at the highest point on the path, we say that it's at an unstable state, meaning that it won't stay at this point forever. Instead, it will move either to the left or to the right. The same concept could be explained by the tipping bucket. As the water flows out from the funnel into the bucket, it gives energy to one side of the bucket, and as it accumulates to a certain level, there will be a sudden release of water flow or energy out of the system. This is the fundamental mechanism of the formation of thunderstorms, hurricanes, tornadoes, volcanoes, earthquakes, and so on. Thanks for your time. Hope you enjoyed it.